Okay, so hello students. My name is Nitin Tomar and I am a PhD student in the Department of Mathematics at IIT Bombay. Today in this session, we are going to discuss some complex analysis problems from the NPTEL course MA 57. I request you in the beginning of the lecture that you may please mute your mics so that everyone can listen to me. Okay. So is the screen visible to all of you? Can anyone just I think it is visible, right?
Yes,
Yes,
right.
right. Yeah. Okay. So what I have done is the correct answers are highlighted from blue, and the false statements, their answers are highlighted via red color. Okay? Is that clear?
Yes.
Yes, sir. Okay. So in this question we are being asked, so suppose that Zn is a sequence of complex numbers. So we have a sequence of complex numbers. So I'm reading question number 1. If we have a sequence of complex number and consider the complex planes denoted by C under the usual topology. So what is the usual topology of the complex plane? That if you have a complex plane like this, so this is the real axis and this is the imaginary axis. Okay. So the neighborhoods are of the form this ball, open ball. Okay. So this is the usual topology. So this so the basis set is going to be the open ball centered at any point of a given radius. Now we are asked that which of the following option is true. Okay. So the first question is, if Zn converges to a point Z naught, then is the limit Zn bar goes is the limit of the sequence Zn conjugate, that is Zn bar, is it equal to the conjugate of Z naught? So the answer is true. Why? See, because if you take any complex number C, okay, so so it is of the form, so Z has this form x plus iota y, right? Where x is the real part of Z and y is called the imaginary part of x. So the conjugate is x minus iota y. Now if I were to ask you that what is the modulus of Z, so it is x square plus y square square root, right? And what if I were to ask you what is the modulus of Z bar? It will be x square plus the imaginary part is minus y. So it will be minus y square square root. So the square root of x square plus square of minus y. But since it is square, so it will be just x square plus y square root. So this is same as mod z. Okay. So which means what we have seen is the following, that for every complex number, the modulus of the complex number is same as the modulus of its conjugate. And here we have used this property. So this is clear why this equality is there, because modulus of Zn bar minus Z naught bar, modulus of Zn bar minus Z naught bar, it can be rewritten as Zn minus Z naught bar. Why? Because conjugate is a linear function over reals. So then it can be written as mod of Zn minus Z naught. Okay. So if mod of Zn minus Z naught goes to 0 as n tends to infinity, this implies mod of Zn bar minus Z naught bar also goes to infinity as n tends to infinity. Hence the first option is true. You can do it by epsilon delta definition also. So we can I'll just show you how to put this thing into epsilon delta definition. Okay. So the languages that I can speak in is are English and Hindi. Okay. So if you have any doubt, then you may please ask in these two languages. Yeah. So for the limit, we have to show, if we were to show it by the epsilon delta definition, we have to show that for all epsilon greater than 0, there exists a stage capital N belonging to natural number such that mod of Zn bar minus Z naught bar is actually less than equal to epsilon for all n greater than n. Sorry, for all n greater than or equal to capital N. So this we have to show if we are to use this epsilon n definition. Now you know that this definition is true because Zn already converges to Z naught, right? So we have this epsilon n definition to be true. So there are so anyway, the basic fact that we are using is that modulus remains same of the complex number and of its conjugate. Now for the second part, we shall use the reverse triangle inequality. It says if Zn converges to Z, it says if Zn converges to Z naught, does it imply mod of Zn converges to mod of Z naught? Okay. So it follows from this reverse triangle inequality. I hope you know reverse triangle inequality, which so it says modulus of mod of A minus mod of B is less than equal to mod of A minus mod of B. Okay. Sorry. So now if we apply this reverse triangle inequality, then we'll get this, right? And now we know that this, because Zn goes to Z naught, Zn goes to Z naught, so this can be made so given epsilon greater than 0, we know that this can be made arbitrary small, okay, for all n greater than equal to n, right? So now we have proved that the modulus of the sequence also converge to its modulus of the limit. Okay. Now the third part is whether or not the converse is true, which means if modulus of Zn converges to modulus of Z naught, does it imply, just a minute. Oh, oh. So those who have joined late, uh, is there some people left? No, I guess. Yeah. Hmm. So we were proving that whether if you are given a sequence Zn such that its modulus converges to modulus of a number, does it imply the sequence Zn converges to Z naught? Good evening, Thangeshwaran. I hope all is good on your side.
Good
Good
evening, sir.
evening, sir.
Good evening. So I may request you to please keep your mic off because there is a yeah. How many participants are there? Okay, there are a good number of participants. Yeah. Okay. So what do you think? You just take Zn. let's say minus 1, and mod z naught, just so if you take zn to be minus 1, right, so its modulus will be 1, and z naught you take all, to be 1 all, then this modulus of zn will be equal to modulus of z naught, which will be equal to 1, right? So clearly in this case, this implies mod of zn converges to z naught. But in the other case, it is not true, right? Because Zn is minus 1. It's a constant sequence minus 1. And we know that minus 1 does not converge to 1, right? It does not converge to Z0. So it is true that if Zn converges to Z0, then the modulus will also follow the same property. But the converse is not true, which you can see via second and third statement. Okay, I hope this is clear. So those who have joined, I have just answered the correct option to be the blue one, highlighted the correct option to be the blue one, and the wrong option is the red one. The okay. Now for the fourth part, if Zn is a sequence of positive real numbers, and if there is a real number which is also positive Z naught, such that this limit holds, that limit of mod Zn equal to mod Z naught, then does this imply Zn converges to Z naught? This is easy, right? Because if Zn and Z naught are positive, then their modulus are equal. So there is nothing to prove in this statement. This is uh, true anyway. Without any effort, one can see that it is going to be true, because in this case mod Zn is precisely Zn, and mod Z naught is precisely Z naught. Okay, so the fourth statement is true. Now for the second statement, this is interesting. See, before going to the fourth statement, I would like to mention few things. I would like to mention few things. Okay, so let me just see if someone is joining. Yeah, okay. There are still students. So if you have a sequence of a sequence of complex number, then you can write it as xn plus iota yn, right? Where xn is the real part of Zn, and yn is actually the imaginary part of Zn. So given a complex sequence, there are two sequences for the real. Okay, so Zn is a complex sequence. Zn is a sequence of complex numbers, and this xn comma yn, these are two sequences of real numbers. So when you're starting with a complex sequence, you are actually dealing with two real sequences. So the question is, so the question that is being asked in this particular question, let me just check if there are more students. Yeah. So please don't join late, because I cannot be looking every time sharing, because I'm sharing my screen. Okay. I humbly request you to be on time, which is 4. Yeah. So let's move on to the fifth statement. It says that if You have a sequence Zn which converges to some complex number, which is obviously every complex number is of the form a plus iota times b. Now, it says, the statement says a sequence of complex number converges if and only if its real part converges to a and imaginary part converges to b. So this statement is true and its proof is given below. And how do you prove it? So we know that you must have learned these two inequality, that real part of z is actually less than equal to mod of z, and actually mod of real part of z and the modulus of the imaginary part of z is also less than equal to mod z. And second, if you have given mod z, which is mod of, let's say, a plus, which you can write it as real part of z plus iota times imaginary part of z. You know, via the triangle inequality, you can write it as imaginary part of z plus real part of z plus mod of imaginary part of z. So the first inequality is precisely the triangle inequality on zn minus z naught. Okay. And for the other inequality, so and the inequality number 2, which is this, so it is just real part of zn minus z naught, right? So I can write it as, so we will apply these two inequalities. So if you look at real part of zn minus z naught, zn minus real part of z naught, the mod, it is in fact equal to real part of zn minus z naught. And we know that real part of any complex number, its modulus is less than equal to its modulus. So it is zn minus z naught. So this is precisely inequality 2 is all about. And the same thing holds for the imaginary part. Okay. Now if we combine 1, 2 and 3, we see that the real part of zn minus z naught mod plus imaginary part is less than equal to 2 times mod zn minus z naught. Why? Because you look at 2 and 3. You look at 2 and 3. These two inequality. It will give you 2 times mod of zn minus z naught. And mod of zn minus z naught, from here to here we have used 1, which is the triangle inequality. Okay. So yeah. So you can see that these two inequalities bounds each other, in the sense that if you assume that that real part of zn converges to real part of z naught, and imaginary part of zn converges to imaginary part of z naught. So this will go to 0 as n tends to infinity, and this will go to 0 as n tends to infinity. But because mod of zn minus z naught is smaller than these two numbers, so it will also go to 0 as n goes to infinity. So these two together implies that mod of that zn goes to z naught as n goes to infinity. And the converse is also true. Why? Because if zn minus z naught, this zn goes to z naught, which means this modulus of zn minus z naught goes to 0 as n tends to infinity. Now these two positive numbers are smaller than this 2 times mod of zn minus z naught. And if sum of two positive number is going to 0, then each of them has to go to 0, which implies this is going to 0 and this is going to 0 as n goes to infinity. So in this case, the first part gives that real part of zn goes to real part of z naught, and the second part in the sum gives the same information about the imaginary part. So using all this machinery, what we have proved is precisely the statement number 5. The sequence of Zn converges to a plus iota b some number if and only if its real and imaginary part converges. Okay. So if you have any doubts up until now, please ask. Okay. Then I'll move forward. Now, which of the following statements are true under the usual topology of complex plane? So we have discussed what is the usual topology. Okay. So if u1 is the open unit is centered at 0. Okay, let's draw here. So this is 0 and this is 1, and it is a open unit disk, so boundary will not be there. So only the inside region is there. Okay. And what else does it say? That u2 is the open unit disk centered at 2. So if this is my 2, so my unit disk will be here, right? Centered at 2. Yes. So this is also open. So which means this one is not included, right? This one is, so it has a, yeah, there is a hole. So one is, what do I want to say? That this one, yeah. So here is one and this one is not included. So the question is u1 union u2 is connected. The answer is clear. You can go by the definition itself. This set u equal to u1 and u2, it can be written as, so if x is the set u1 union u2, if x is u1 union u2, then the definition, from definition u1 and u2 are both open and they intersect trivially. They have empty intersection. So by the definition itself, X is not connected. What is the definition of a set being not connected? That this set can be written as a disjoint union of open sets. Okay, under the induced topology. So this set is not connected. Now the question is, when you take the closure of each of these sets, so the thing is, when you take the closure, the boundary also gets, so this is u1 closure and u2 closure will also be, so the boundary will be there. So this is my u1 closure union u2 closure and this is 1. Now it says is if the union of the closure is connected. Okay, so we know that, what do we know? That every path connected set is connected. So we will show that this u1 union u2 is actually path connected. How do you show that? You take 2 points. So either these 2 points can be in u1, right? So if they are already in u1, you can always join them by path, right? Okay, let me make the diagram more clearly. Please mute your mics. Who is this? Yeah, okay. Thank you. So if you are taking any 2 points in u1 closure union, these points you can always connect. Other possibilities, both the points lie in u2 closure. Again, you can connect them. And the last possibility is, if one point is in u1 closure and another point is in u2 closure, then can you connect them? The answer is yes. Why? You go to 1 because 1 is also the set in the set. So from this point you go to 1 and from 1 you can always go to this point. Okay, so this way this set is path connected and therefore connected, and this is precisely what is written in language here. Okay, so this is true. Okay, yeah. Now the third question is, does there exist an open set of C which is compact? If you have read, so if you know the, okay, someone is joined. So there exists an open set of C which is compact. So see, the complex plane has only two, because C is a connected set, and any, so the only, so compact implies it has to be closed, right? It has to be closed. So the set we are looking for is both open and close. And in the complex plane, because it is a connected set, there are only two sets which are both open and close, which is empty set and the set itself. Okay, but C is not compact, right? C is not compact. This is not compact, so you cannot take this as an example. But empty set, it is open and it is compact. Why? By definition itself. Okay, what is the definition of compactness? Every open cover has a finite subcover. Since empty set has no elements, so any open set is an open cover. Okay, the empty set is both open and connected. Okay, so there exists an open set of C which is compact. Now the fourth question is, are compact sets always closed? The answer is yes, and this is a well-known theorem known as Heine-Borel theorem. Okay, so this statement is true. Now fifth one is interesting. It says, if you have a disk, okay, d0r means it is a disk of radius r. Okay, it is a disk of radius r. Now it says, if you have a sequence of compact set xi's, if if you have a sequence xi in this d0r, so remember d0r is open. Okay, it is the open ball centered at 0 of radius r. So this will be denoted by this. Then so each of these xi is compact. Then the claim is, then the question, in the question they ask is whether this, their union will be compact. Okay, so the answer is false. Why? Because you take just r by, for example, if this is your xn, the sequence of set is xn, you take xn to be r by n. Okay, now this union of xn, it will be r by n, where n belongs to natural number, right? Is this set closed? This set is not closed. Why? Because 0 is the limit point. R by n goes to 0 as n goes to infinity, right? So this set is not closed, hence not compact. Okay, so this example we you must have seen also in real analysis. This example is the prototype. So for example, if you have 0 here, then you consider the sequence 1, sorry, half, nothing is here, then 1 by 3, and you keep on doing that via the sequence 1 by n. So if you take this sequence 1 by n, this is bounded, but this is not closed. Why? Because 0 is the limit point of this sequence, but 0 does not belong to any 1 by n. 0 does not belong to this set. Okay, so this option is false. So union of compact set need not be compact. Okay, so the correct options are 2, 3, and 4. Okay, any doubt up until now? I am open to doubts now. If you have any doubt, please ask. Okay. 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 Assuming that you people have no doubts, so let's move on to the question number three. So the question number three is, which of the following statements are true? So for every z in C, does the real part of z of 7, so z power 7, if you are starting with a complex number z, then z power 7 is again a complex number. You can consider it real part, right? And you can also consider real part of z. The question is, does this 7, the real part of z power 7, does it equal to the seventh power of real part of z? Okay. So the answer is no. Why? Because you just put iota in place of z, iota power 7. Okay. So here real part of iota is 0, so 0 power 7 is 0, but iota power 7 is minus 1. So real part of minus 1 is actually minus 1. So these two are not equal. So this statement is false. Okay. So this is what I have written. Now the question is, does z bar power 7 is actually equal to z 7 bar? Okay. The answer is true. Why? Because the power splits. The conjugate of two complex number is actually the conjugate of product of two complex number is actually equal to the product of the conjugates of the complex numbers. Okay. Or one direct way to see this is you just assume the polar form z equal to r iota theta. Then z7 will be r7 e iota 7 theta, or how do you write 7 iota theta, and z bar will be re minus theta. So this implies z bar power 7 is actually r7 e minus 7 iota theta. And if you take here the whole bar, it will actually be r power 7 and e power minus 7 iota theta, because the conjugate of e iota theta is e power minus iota theta, and these two are same. Okay. So this is true. And third is, a complex number is real if and only if the complex number itself is equal to the conjugate of itself. Okay. We know the complex number is real. Any complex number can be written as real part of z plus iota times imaginary part of z. This is real if this part is 0, right? If z is equal to real part of z, so if z is equal to real part of z, then if if z is equal to real part of z, then z bar will be real part of z bar. But because real part of z is a real number, so its conjugate will have no change. So this will be real part of z, and which is z itself. Okay. So hence this is true. So this statement is true. You must have seen this many times. And fourth statement is also standard. If you take a quotient of two complex number, of course w has to be non-zero, and you take the conjugate, it should be conjugate of w in the denominator, conjugate of w in the numerator is conjugate of z, and in the denominator it is conjugate of w. So this statement is always true, and the proof is only computational. Okay. Now the fifth one is interesting. So fifth one says that, does this statement holds? If you have two complex number, then does modulus of z plus w square is equal to modulus of z square plus modulus of w square? This statement is not true. Why? Because you take z equal to 1 and w equal to minus 1. So LHS will be 0, right? And RHS will be 2. So this statement is not true. You can check. But there is more to this statement. If we look if we look closely, by the definition of inner product, this modulus of z plus w square, it is actually equal to inner product of z plus w with itself. Now if you open the inner product, it will be, sorry, it should be 2, it should be, yeah, it should be mod z square plus mod w square plus 2 inner product of z comma w. Oh no, it should be, here we should have 2 times real part of z comma w. Now if z plus w square, it is equal to mod z square plus mod w square, then this part has to be 0, which is not always true. Okay. So, and anyway, we have one example. You just put z equal to 1 and w equal to minus 1, and you will see that this equality does not hold. So, this was the MCQ part. Now, let's move to some computational part.
Hello, sir.
Hello, sir.
Yes, yes.
I have
I
a
have a
doubt in the
doubt in the
first
first
statement of
statement
this
of this
question.
question.
Okay, just let me. Okay, just a minute. Yeah. Is this 7 power?
Yes,
Yes,
we have
we have
considered
considered
z is
z is
equal to
equal
y.
to y.
So z
So
Okay.
z
raised to
raised to
7 will
7 will
become
become
minus i.
minus I.
So how
So
would
how
the
would
real
the
part
real
of
part
z
of z
raised to
raised to
7
7
becomes
becomes
minus 1?
minus 1?
Oh, have I done something? Just a minute. It is. No, no. I think this should be okay. What is z? Okay, if you take z power iota, what is z square? It is minus 1. It is minus 1. Then z6 will be minus 1 cube. It will be minus 1 itself, and z power 7 will be minus iota. Okay. Oh, so this example is not working, huh? Okay, okay. Let's forget about this example right now. Let's see this in generalities. If you take z to be r e iota theta, okay, what will be z power 7? It will be r7 e7 iota theta, right? So real part of z power 7, it will be actually equal to r7 sine 7 theta, right? Is this clear?
Cos
Cos
7
7
theta.
theta.
Oh, sorry, yeah. Cos 7 theta. Now, if you take real part of z, what it is? It is r cos theta, right? Now, if you take it 7 power, it will be this. So, it is r7 and cos theta power 7. So, for them, these two quantity to be equal, you need that cos 7 theta should be equal to cos power 7 for all theta, right? Hello. So yeah,
Yes,
so
sir.
Yes, sir.
so we know that this won't be true in general, right? So this does not hold in general. You can always choose some theta for which this inequality won't hold. Okay, is it clear now? I think I made some mistake with one example. Is it clear?
Yes, sir.
Yes, sir.
Okay, thank you for pointing out the mistake. Yeah, yeah, this is yeah, this is more or less, this is more like a discussion. Okay, we all are learning mathematics here, so be this time of 1 hour as a discussion hour. Okay, now the question is, if you have a 2 plus 14 iota and in the denominator 3 minus 4 iota, then what is your imaginary part of this particular complex number? You know the trick, right? You just rationalize it. This process is called rationalizing, or whatever you say. And in the denominator you will have a square minus b square type identity, so it will be a square minus, yeah, okay, yeah, yeah. So you compute all these things, 14 iota, okay. So can you compute these things? Should I leave, or should I do the calculations? I mean, this is just complex multiplication, right? In the denominator you will have 9 minus 16 iota square, and it will give you this will give you 25 something, and you please fill the denominator, numerator, and you will turn it, so it will be in some form a plus iota b, okay. This b will be your imaginary part. If assuming that I have done the calculations correct, then this is going to be the answer, okay. So fifth question the fifth question is, you have to find the power of this complex number 2021. So you know that the power will go down, right? Like, because z, if you have two complex number, the modulus splits. So by induction you can prove that mod zn will be, the modulus of z power n will be the nth power of modulus of z. So this is precisely what we have written here. So this can be written as 12 minus 5 iota upon 13 mod 2021. Okay. Now what is the mod of this complex number? It will be 12 by 13 square plus minus 5 by 13 square square root, right? Now this will be 144 plus 25 by 169 root, and this is just 169 by 169 root, and it is nothing but 1. So 1 power 2021 will be your answer, which is nothing but 1. Okay. So okay, so this I have written all the calculations this time. So is this clear? I am open to doubts. After every two questions, I am open to doubts. If you have any doubt, please ask. Otherwise, I will go forward. Okay, seems that there is no doubt. Yeah. Also, if you have any suggestions, then you may please tell me. Okay, so I'll draw. Okay, let's remember the complex. So these are two complex number, 1 plus 2 iota and 2 minus iota. It says consider the parallelogram Q in the complex plane with one vertex in the origin and whose adjacent sides are given by Z and W. Then the question is, what is the area of Q? Okay, so we can draw here somewhere in the corner. Okay, I'm drawing in this corner. Okay, I will be needing some space because I have to show minus 1 also. So 1, so 1, 2, 1, 2, 1. So my 0 is here. My Z is 1 plus 2 iota. Sorry, 1 plus 2 iota, right? So this is my 1 plus 2 iota. And then I have 2 minus iota, which is 2 minus. So this number is 2 minus iota. So you join. So the question is, if you join these 2 points and consider the parallelogram drawn by it, okay, so this is my Q. This is my Q. Okay, just to avoid the confusion. So this was my Z, mod Z. So this was my W, this was my Z. So this is my mod W, this length, and this length is mod Z. So the question is, what is the area of Q? You first of all note that this Z and W are orthogonal. Okay, why? If you compute Z comma W, what it is, what 1 plus 2 iota comma 2 minus iota. And how do you take the inner product in the complex plane? You multiply the corresponding parts. Just a minute. Yeah. So it is 1 times 2, 1 will multiply it by 2, plus 2 times minus 1. So it is 0, right? So these two are perpendicular, and which is also visible in the figure. So therefore Q is a rectangle, right? So what is the area of the rectangle? It is mod Z times mod W, right? This is the area of the rectangle. The area of rectangle is nothing but the product of the length of the adjacent sides. Okay. Yeah. So if you compute mod Z and mod W, it will come out to be root 5, both of them. So it was in fact a square. So the answer will be 5. Okay. So the area of this Q is 5. Now we have come to the seventh question, and this is one interesting question. So if you have a non-empty subset of C, and if you have a sequence Zn is a sequence of a complex number. Now the question is, which of the following statements are true? Again, just to remind you, the statements which are false, I have given their explanation in the red color. The statements which are true, I have given their explanations in the blue color. Okay. So the first statement is, if X is bounded, there exists a subsequence which is convergent and whose limit is in X. Okay. So the answer is no. Why? Because even before this, we saw one example. So you okay. So you take open unit disk. So open, let's say centered at 0, and you take your the given sequence Zn to be minus 1 by n. So it will be sequence. So Z1 will be here, Z2 will be there, and so on and so forth. It will go like this. So it will go towards 1. Okay. But the Zn, so the sequence Zn converges to 1. If a sequence is convergent, then every subsequence is convergent and to the same number itself. So the sequence Zn converges to 1, which is clear. Why? Because Zn is 1 minus 1 by n. And hence every subsequence will converge to 1. But does 1 belong to set X? No. Okay. So it is not true. It is not true that for a bounded set, it need not be true that convergent sequence, every bounded sequence will have a convergent subsequence. But if you remember from your real analysis course, there is one statement which is true related to this. And it is, if X is bounded, if you're starting with a bounded sequence, then it will have a convergent subsequence in the real number itself, right? Now here we are dealing with the complex field, so the same statement holds for the complex plane also. And this is precisely what we call the Bolzano-Weierstrass theorem. So, so, so this is my Bolzano-Weierstrass theorem. So the major difference between 1 and 2 is this part. In the first part, it was asked that, okay, in both the question we were given the bounded set X, and the same thing was asked whether or not every sequence will have a convergent subsequence. But the main difference is the convergent in what? In the first question, it was convergent in capital X, and in the second part, it is convergent in the complex plane C. Okay. So the for the first we saw one example, 1 minus 1 by n sequence. But for the second, the statement is true, and indeed it is the well-known Bolzano-Weierstrass theorem. So keep in mind these two things, the major difference between the first two options. Now the second question is, if X is closed, then does the first option holds true? In the first option, if you replace boundedness by closeness, does it hold true? Here we have boundedness. If you replace it by closeness, then what happens? The answer is still false. Why? You take X to be the complex plane, and you take sequence Zn to be n. So this is closed, right? The complex plane is closed. Now this is a sequence Zn. Does it have any convergent subsequence? No, sorry. Here we should have just a minute. Yeah. So you see that the difference between any two elements in this sequence it at least one, right? It is at least one. So it cannot be Cauchy. And if it cannot be Cauchy, then it cannot be convergent. Forget about whether or forget about talking about it limit. It's not even convergent. So we won't even go to the limit case also. Okay, so this statement is utterly false. The one thing that I need to change here is this following that yeah, it should be greater than X. Yeah. Now, if X is compact, then Zn has at most finitely many points. Okay. So if X is compact, then Bolzano-Weierstrass theorem, if you have if you have known about the compactness and sequential compactness in the metric space are same. So if X is compact, then this sequence Zn, it will have a convergent subsequence. Okay, this much is guaranteed, because compactness and sequential compactness are two same notions in the metric space, and since complex plane is a metric space, hence this is true. But the question is whether or not it will have finitely many points as the limit points. So the answer is false. Why? Because if you take, let's say you take open unit ball again. Okay, so X is this closure. So this is my open unit ball, and you take its intersection with rational. Okay, now we know that it is a countable set, right? Why? Because rational is countable, and it is a subset of rational, so it is countable. So you can, any countable set can be written as the enumeration of something. So it can be enumerated. So I am consider this to be my sequence Zn. Okay, so this Zn, it is a sequence and X is compact. Now what is the closure of this? So its closure, if I ask you what is the closure of rational in the real line, you will say it is the complete real line, because rationals are dense. Now we have collected all the rationals in the closed unit disk. So its closure will be the closed unit disk itself. So does it have finitely many limit point? No. The answer is clearly no. Every point in the closed unit disk is a limit point. So this answer is false. And the fifth is again what I told, that every sequence in X has a convergent subsequence whose limit is again in X if and only if X is compact. So the first part before the if and only if, it is called the sequential compactness, and in the metric space sequential compactness is same as the compactness. So this option is true. Okay. So with this we finish the assignment number 1, and if you have any doubt please tell me. Is there any doubt?
No,
No,
sir.
sir.
So
So
far, no
far, no
problem.
problem.
Okay, just a minute. Someone has asked one doubt. Okay, on 1.6. In 1.6, what if the complex numbers are not orthogonal? What is the area of in which 1.6? Consider the parallel. Oh, okay, this question. What if the complex numbers are not orthogonal? How will you write the area of the parallelogram in terms of ZW? Hmm. So you have many techniques for that. You can use double integration technique. See, this question was to make sure that you realize that this is a parallelogram whose adjacent sides are orthogonal, in which case this becomes a rectangle. Okay, and its area is easy to compute. But in generality, there is you have many techniques to compute the area, and one of them is double integral, which you must have learned during your what should I say, BSc, uh, during your BSc days. So for example, if you have any parallelogram, let's say this is a complex plane and this is any parallelogram, right? So any parallelogram, let's say this is y1, this is y2. So you can use your double integration techniques, right, with dx dy with appropriate limits, and this will be your area. Okay, so this will be some x equal to let's say 1 phi to y, some function of y. So your x will run from phi 1 y to phi 2 y, and then your y will be from y1 to y2. Okay, so this way you can calculate the area even when they are not orthogonal. Okay, any other doubt? Is that clear, Ravi Shaw? If I'm Ravi, is this clear? Ravi? Okay. Okay, any other doubt? But I want the answer in terms of Z and W. No, the answer will not be in the term of Z and W, because if you fix two complex numbers and you're asking to compute its area, then it will be a numerical value, right? For example, we can always do this question also with the double integration technique. You have all these techniques, so when it comes to a strange problem where you have no orthogonality between the vectors, then you can always go to these techniques, and your answer will not be in terms of Z and W, because you are fixing your Z and W first. So your answer will be a numerical value. Ravi, is that clear? If you want some closed type formula, like for example, for rectangle, in this case it was mod z times mod w, then it will be more difficult than this, finding the numerical value. But still, this double integration technique can be used there also. Okay, any other doubt? Yes, Ravi, it is possible to find a closed formula. You can always I think for parallelogram it is going to be much easier. Okay, so what is the area of the parallelogram? Do you know this? See, the thing is, we don't want to use. I mean, the basic idea here is to apply the new theory that you are learning. Okay, you can always go back for easier questions into the previous theory, but the idea is to develop your intuition on the basis of the new theory that you are learning. Okay, any other doubt? So if you have no doubt, then I think we should close the meeting. We'll see you next week. If you have any other doubt, then I'm here for a couple of few minutes. You may please leave if you have no doubts.
Thank you so much, sir.
Welcome, welcome. Welcome, Nandita. So I will upload this video on my YouTube channel as soon as possible. Okay. Welcome, Thangeshwaran. Welcome, Dipali. Okay, then. Bye, guys. Bye, students. Okay, is there any interpretation of the cross product in terms of complex multiplication? Hmm, just a minute. Okay, I'll I'll be just back in a minute. You please stay there who have doubts. Yes. Yeah. So what was your doubt, Ravi? You can speak now. I mean, there are not much people, so you can speak. Okay, so let me just answer this question. My YouTube channel. Okay. So you just type this Nitin Tomar PMRF maths complex analysis. Complex. You will find on YouTube. This recording you'll find on YouTube. Okay. I'm not able to speak. Okay. So Ravi, your question is there any interpretation of cross product in terms of complex multiplication? So the answer is yes. Yes, there is, because if you realize what is a cross product, so when you take cross product of two vectors, it just give you the vector in the direction orthogonal to both of them. Okay. So if you have two vectors, then cross product of these two vectors is going to be a vector which is orthogonal to both of them. So in the complex plane, we have the concept of orthogonality. So these two notions can be solved, and I will to reach to a point where your answer to the question will be yes. Yes, there is an interpretation of cross product. So cross product can be defined anywhere in the inner product space formally, mathematically, in the sense, because we just need orthogonality. As long as you have orthogonality in the system, forget about the complex plane. Just even if you land somewhere in the inner product space, complex plane is a particular example of inner product space. As long as you have a notion of orthogonality, you can always talk of some interpretation of cross product. Okay. Okay. So yeah, if you have, okay, then yes, as I said, like you can write down the formula of a parallelogram in terms of z and w. This particular question which we saw was one particular example and one very easy one, because in that orthogonality was there. I mean, they were perpendicular. As the area formula is A cross B. What is A and what is B? Can you tell me what is A and what is B? Okay, I'm stopping sharing my screen first. Just a minute. Yeah. Yeah, Ravi. Just a minute. Let me open my Google Meet in this account. A and B are the length of the adjacent sides. See, earlier you have to verify this, but earlier what I want to say is, as you're progressing with your mathematical journey, there is, at that time I didn't tell you, but there is already a closed form formula in the literature for area of parallelogram, right? It is just base into height, nothing else. So if you are given any polynomial, any parallelogram, you can always have base and height in terms of z and w. Okay, so yeah, I mean, so in that particular way, you can have a closed formula for the area of a parallelogram. Does this make sense to you, Ravi? Yeah, because you just okay. Yeah. Any other doubt? Okay, if you have no doubt, then I'm closing the meet. We'll see you on next Saturday. Okay? Bye.